Well, good afternoon. I kept my promise to talk about the barium titanite cylinders that I got a long time ago, as well as the delay lines and other things off of warships. So I have it hooked up to radio and scope. Let's move this a bit, because a bit of interference from iPad running on this too. Now look what happens when I touch the cylinder. I guess we'll get closer, right? So best to describe it, if I can, I have to put this around somewhere to do it, I suppose. Yeah, still got the wafer material in there that's broken off. Oh, wow. I did that. It really got active. I'll have to show you that one. So I'm holding it. I touched the wafers inside. Take my finger out of the center of it. I'm getting about 9 to 10 volts. Put it back on the table and see what okay. Pick it up again, move it around. Put my finger inside where the wafers are and press on it. Take my finger out and go down. So these things I made a long time ago. Not the cylinder itself, I got those from a surplus store, but I got the idea to put in a delay line, kind of out of the, which are a bunch of wafers, 30 millimeters in diameter, as well as 1/16 of an inch thick or thinner. Stack them on top of one another, and I had deposited some rare earth materials and other things and tried it out, and it did work just by thinking about it. I thought maybe I should try these delay lines I found on a Navy ship in the sonar room. The Jezebel system, it's called, on HMCS Yukon. A little different on Saskatchewan and Columbia, as well as Mackenzie ships, Saskatchewan. I played around with it. I got investors come to me. The Ria Trade Business Group, they got scammed by somebody that had a magnet on a piece of wood and claiming over unity and all that stuff. So I made one out of these cylinders, about 8 of them, in a circle, and had them discharge at different rates. And they were very happy with that, and they mentioned it to the main, secondary investors who were Chinese, but the Chinese never showed up for 24 million to put into it. Then that dropped away. Then I went to Japan, and it was funded for $2,400,000. And I gave them to the Japanese. They tested them, and they're on video. We tested them on video. The Kyoto Institute of Technology measured 18 kilocycles that these things are making. What do we get here? Something like that. Let's turn this up a bit. Move it along. Side bands and other things. Getting a ham radio operator in there. Not now, but we'll go on. Right there. Well, that's its RF frequency it's putting up now. Put your finger in there, not much happens, but it's resonating at that, and it's capable of producing on its own. Turn this down a bit. 10,000 to 20,000 volts, as demonstrated by Pierre Sinclair in Canada as well as myself. Good hefty spark like that, bang. So you got a spark going like that, great potential. So how do you sort of make that into a longer lasting situation with a lower voltage? I figured that out with delay lines, much like Collins mechanical oscillators and that kind of thing. Delay lines, old vintage stuff. The delay lines were in crystal ovens and that kind of thing. And I took those apart, got these out, tested them. I had a lot of time to play around after my work on the warships. I do that mostly in the evening, got nothing else to do, kind of play around with these crystal stuff and made these power units for the Japanese and other folks. I was funded about 5 times to make them, but they could not find investors to go into manufacturing these things, so it wound up kind of dead, and this thing was found a while ago in a crate I had. It's very heavy. You can sort of see the wafer stack in there. See the square piece in there? That's the wafers pushing against the sides of this here, and when I do that, when I put my finger in there, of course it changes quite a bit, and I move it around the wafer stack. There used to be a tuning in it on top here that I would adjust like that at different angles, putting pressure at different angles like that on the crystal wafer stack, which was loaded into a plastic container, so it's very delicate loaded. Had to be very careful when I'm doing this stuff. I'm getting spikes on its own here for some reason. Okay, I'll go up close. Oh, that's interesting. I wonder what's going on. Ferromagnetic properties this stuff has, as well as other properties, of course. Ferromagnetic properties and piezoelectric properties and even magnetic properties, kind of thing, which I just mentioned. Well, that's interesting that it goes up and down, so I'm going to wave my hand like this. I'll blow on it. Bit of deviation. That's when I gently touch it. You can see the spikes. Hopefully you can see the spikes. I didn't do anything. I didn't touch it. It's got spikes going there. Hello? Picked up my voice, I think. Hello? I thought it did. Oh, I didn't do anything. That's a big spike. Okay. I'll try that again. Maybe it's a bit. 1, 2, 3. Okay, some seconds in that. Oh! Wait a minute. It's just dragging along here. There it is again. The same spike. So electrical potential. When manufacturing this material, one of the main problems is that the Casimir effect energies get involved with it and causes problems. I have that on my blogger. Waiting on the edge of forever, somebody can break into it and use that information. It's a very detailed article on this. Also, Dr. Franklin E. Mead had a patent in 1996, December 31, on a zero-point energy collecting device, which is barium titanate as well. I don't know if that's ever got off or when they were, but it's interesting that IBM bought up all the patent rights to it, and I guess they're working on it. Of course, the government folks, government labs are working on this stuff quite a bit. So, but anyway, in my travels to Japan, also very successful customers, happy customers, as well as the German people that came around and invested another $250,000 with me, and then there was an English fellow that did the same. 50,000 or 75,000. I think Ian got some money from him too. Richard Brewer. I don't want to name too many names. Well, I can name them, but I might get in trouble by those people. Now it's gone funny again. Okay. It's definitely picking something up. It's very active right now. And it's getting quiet again, so... The audio from this is pretty cool, too. I used the audio in, as you look at one of those videos on YouTube where I'm levitating stuff with this thing around it and inside of it. You'll see that video. That was in, when was that made? In the 90s, I think. So I decided to drag this thing out today. I could redo it, but, you know, I get about, the maximum I get is 3 volts at a couple amperes, okay? That's because I have delay lines, all the crystal stuff inside, as well as capacitors and reactors and that kind of thing, and all small, but let's just see how we tested it years ago. It's on Nancy's YouTube channel. It's not really a free energy. I don't know what you want to call it. I call it converter, not free energy. Free energy is kind of a misconception. It's just something John J. Searle made up, or some idiot made up. Let's move this along here more. We'll crystal phase it as well. That's called crystal phasing. Oh, okay. I use radios like my sixth sense for monitoring everything, the ionosphere, the magnetosphere, the solar flux index, plus earthquakes. These old radios work perfect. Vacuum tube type. Older the better. Regeneration type receivers. And I always use them for doing stuff like this. I heard that cracking sound. I wonder what that is. Car ignition somewhere outside? Maybe. I'm going to pick this up now. Watch the scalp. Put it down. I heard another click in there. There's something going on somewhere. Let's put iPad close to the receiver. Nothing to us. Can we pick up the funda? Oh wow. 12 volt maximum scale. Drop goes up and down because the crystals are all kind of messed up in there and kind of cracked up. I'll give it a good bang and see what that did do. Oh, there you go. 1, 2, 3. Didn't improve much, but I put pressure on the wafer stack. Okay, my fingers in there, put pressure. It's not doing much now, but I'm moving it around a little bit. There it goes. About 12 volt. And milliamps, of course, but nothing spectacular. Now take my finger away and go away from it and it drops. And my fingers are here. It's changed now a little bit. Oh, interesting. Okay. Getting a lot of spikes. So I'll try and get this as close as I can. kind of, this whole thing is damaged, you know. Inside the crystal stack is damaged. I'm pressing on it, as you can see. Take my finger away. Press on it again. Oh, and then put a toilet paper roll in it. Press on it. Hear that cracking sound? Pull that out. Yeah, so that's the barium titanate story, kind of. I turn this down. Kyoto measured 18.5 kilohertz. I'm measuring it at under that now. Oh, it's only way down low to about 8 kilohertz, roughly. Let's turn it more. Crystal phasing it. Oh. More crystal phasing. RF gain. Turning this section here. All right. Turn that down. Let's play with the scope a little bit and see what happens. Oh, slow moving thing, you know. Got a memory that's got to erase. I don't know what I did do, but I turned it this way. Kind of slow, isn't it? Let's move it this way. Ooh, that's interesting. Let's see. Taking its time, and again, it's got let's go back a bit. It's slow, but that's okay. Used to take this scope, used to take floppies. I don't have floppy, I'm just going by instinct on this thing. Let's do this. Let's increase that a bit, huh? How far can I increase it? Pretty more sensitivity. I'll press on the crystal wafer inside. Stack of. Oh, that kind of goes thinner. Take my hand away. Kind of overdoing it here, aren't we? Turn that down. Maybe resonating like fundamental frequencies. Sometimes they're involved and can fool you quite a bit. Let's turn that down. Do that again. Oh, we're getting other frequencies here too. Somebody's here, I don't know who. Let's see, somebody around here. Oh, hi. Alright, I'm gonna turn this off.